All right, well, it's hard to believe that we've already come to the last, but certainly not least, talk in our inaugural Advanced Users Group track. And we have two of our esteemed LabVIEW champions to present on a very important topic of code optimization and benchmarking. And one in particular, Christian, is very well known for writing very fast code that somehow manages to still fit inside this postage stamp on this block diagram. And so he might be under the impression that he volunteered to give this talk this year, but I'll let it be known that had he not volunteered, he would have still been giving this talk this year. That would have been my one prerogative of session chair, was that this man must be here and speak about how we write fast LabVIEW code. And so with that, we are going to get started. My head is already getting filled from like 2 days of these amazing talks. And so we've got room to squeeze in one more hour. So with that, I'm going to let Ed Dickens kick it off. Thank you.
All right, good afternoon, everybody. Ed Dickens, I work for a little alliance member up in Iowa, Distech Integration. I've been there for about 15 years. We've been an alliance member for 12 years. I agreed to take the load of the benchmarking portion of this talk off of Christian's shoulders so he could concentrate on the optimization part, which is probably why you're really all here anyways. So my part's going to be pretty short. I think I only need maybe 10 minutes or so, and then I'll turn the mic over to Christian. All right, quick little agenda. We're going to talk about, everybody's done benchmarking, I'm sure. You probably dropped a flat sequence structure, a couple of tick counts, and some code in the center, calculated a difference. We'll go over just real quick some of the problems with that. Maybe a few coding standards, things you need to look out for. A few little mistakes, VI settings, LabVIEW settings that you might need to watch out for. And then kind of a better way to set up that benchmarking code so you get good results. And optimization, I think Christian probably has some more bullet points for his part, so we'll just kind of let that sit and let him cover it when he gets to it. All right, so we've probably all seen this, probably all done this hundreds, if not thousands of times. Super easy way to benchmark your code. Like we say, you drop that flat sequence structure down, a couple of tick counts in there, subtract the difference in the time, your code's running in the middle, you get an output on the time. A few little problems with that. You can get a much higher time resolution using this high resolution relative seconds VI rather than the tick count VI. You'll find this in the timing palette. It's a nice supported function. You'll get the value of the second timer, on your particular PC out to 14 digits of precision. So you're lost my train of thought. Sorry about that. It says in the help file for this, you can use this VI to get much higher. I am just falling apart here. Use this VI to take precise time measurements over short periods of time. You can use this VI to benchmark code with very high precision. It actually says that in the help file for this function. It does also say avoid using this VI to take measurements over very long periods of time. And the reason for that is it has a much higher clock drift than some of the other time functions. This is a little plot of clock drift over about a 3-day period. The green line represents that high resolution relative time, and you lose about 4.5 seconds, or it drifts about 4.5 seconds over that 3 days. The tick count is the red line, so you only lose about 1.5 seconds. The white line on there is actually that get date time function. That one looks a little funny, and we think what that is there's an OS behavior in there that tries to resync that, since it's actually getting an actual time instead of just basically a second counter. It tries to resync it to an NTP server, and so as it starts to drift off, it brings it back up. So that one's probably not a good one to use. But over a short period of time, you will get much better precision using that high relative seconds VI. If you're building any code that's taken more than 3 days to run, then you'll probably need to really pay attention to what Christian has to say there. A couple of things you need to watch out for when you're benchmarking your code. Constant folding. You probably all know what constant folding is. If you look at your code and you have this, these options turned on in the LabVIEW help or the LabVIEW settings, show constant folding on wires, show constant folding on structures, you can get these little squiggly marks on the wires here that show, well, that I can figure out what this is at compile time and not actually have to run that add function. So if we got 12 and 2 add, it's always going to be 14, so the compiler will actually change that to be just 14 and just kind of eliminate that whole add function. You can also get constant folding on structures, and there's a few settings that actually can affect this. The exact same structure there with a constant will be constant folded if you have debugging enabled. Did I say that right? If debugging is disabled, you're right. If debugging is disabled, it'll constant fold out that entire structure. And you can tell that with the hash marks on the inside of the structure. Now, if you have debugging in your options enabled, it's going to assume that maybe you need to drop a probe inside that for loop, and so it won't do that optimization for you. So those are some things you need to think about. And if you remember back on that original slide where we had that simple flat structure, we were feeding in a couple of constants into there. If you're not going to be feeding constants into your code that you're going to run in your final application, make sure you're not doing it while you're trying to benchmark it, because something like this could happen and that will affect your results. Another thing that can happen, another compiler optimization, it's called dead code elimination. And this is the compiler trying to get rid of code that's not used. And I've actually got an example showing this, but basically what it is the algorithm in here is fairly complex. This is trying to find prime numbers. If the output is not wired, the compiler will look at this and say, well, I don't need to compile that, let's just eliminate it. And so the whole thing can just literally go away. So if I can get over to my example. And I have to drag it one way or the other. There we go. All right, so what we have here, and some of it's hidden, of course. I've got to look over my shoulder and find the mouse there. Be patient with me, we'll get there. Start out at a smaller resolution. There we go, okay. So on the block diagram, which way I got to drag this? We have this sub VI, and that green sub VI just contains that code you saw on that slide, and it's just finding prime numbers. The output of the sum of all the prime numbers it finds is wired out of that for loop. And this is hard to do over your shoulder. So what we're concerned with here is the sub VI and its settings. Right now, this sub VI is set to inline itself when this is run. And again, that's another setting in the VI properties. If you haven't seen that one, and I'm sure the properties are going to open on the wrong screen again. Drag this to the VI properties. Execution. Here we're set to inline this sub VI. So that basically, when this runs, it's going to eliminate the sub VI and put the code on the block diagram of the other VI. So that's kind of an optimization you can do to get rid of that VI overhead call. In the second case, we have the exact same thing, but that output for the sum of all the prime numbers isn't wired. And what this is going to do if I run this first one, this is the one with the output wired, and with the input we have here, this is going to take about 1 second for each iteration to run while it calculates all those numbers. And it's going to plot the results. We see sometimes pop up here, the average time, the max, and the mean time. And you also notice on the very first run, took a little bit longer. I'll mention that in a second. The second case where we didn't have that output wired, the exact same VI still in line, if we run that, all of that code was eliminated. So this is something you need to watch out for, because if you get some results that look a little unrealistic, you might need to take a second look. Now that's not always going to be the case. It's not a hard, fast rule. In the other cases, I have a simple timer also inlined, and also on the wrong screen again. There we go. So all it is our high resolution timer, a wait function, outputs the tick count. And again, that is, one of them is wired. So we run this one, we've got our delay set at 1 second. Should take about 1 second for each iteration. It plots them all out there. This bottom case shows that same thing with that output not wired. We run it, and you'll notice this one actually does run. So it's not eliminating that code, even though all it is a simple wait function. So this is something you need to watch out for. Again, it's not something you can say, oh, I have to wire it, or oh, it's just going to always do this certain behavior. It does change based on what the function is in there. Trying to get back to my presentation. There we go. All right, so some of the things that you might want to watch out for in the VI settings. A lot of these are just things that you might normally do just for general efficiency. Updating indicators, having indicators in a loop, constantly updating is going to slow things down. That debugging setting is going to add all those debugging hooks in your code so you can drop probes, execution highlighting. Those can affect the overall time, and they can kind of introduce some jitter in there. Make sure you're not executing code in parallel. Don't try and benchmark two things at the same time, of course. Auto error handling can cause some problems in there. And some things you might not think about, especially if you're like running on a laptop. If you're running on batteries, you don't have it plugged in. Some of the power settings can step in, reduce the maximum speed of your processor. Sometimes your IT department can step in and limit some of those things. A lot of those people like to overstep their bounds. Also look out as you're pumping data into your VIs. If it's going to be various data going in that you're analyzing, use random data. Use different size data sets. Don't always use the same thing. Make sure you know what the results should be on that data set. But change it up a little bit. Having the front panel of the VI open while you're benchmarking it can affect it. And so what you should do is take that code that you want to benchmark and close it in a sub VI. Put that on another VI, and I got a slide of that coming up here. So that it's being called as a sub VI instead of just and the front panel of it is not open then. The first iteration of your code, let's see if I can get, I closed it. Yeah, we'll just skip it. The first iteration of your run can have some longer results that could artificially increase if you're looking at an average time. It will also be, it's generally the longest run. So you usually want to throw that out. File I/O, memory management, all sorts of things can affect that you probably don't normally care about. You might want to look at minimum and maximum times, as well as the average times. You can do whatever kind of analysis on those times you need. If you're running this on a single computer, there might be something specific to your computer that might make it run either faster or slower than other computers. If you have other computers to run it on, give that a try, see how it works. If you're going to have this running on a dedicated machine, say this is going in a test system and it's a one-off test system, do your benchmarking on that machine instead of on your development machine, just so you know how it will run on there. If you don't have a lot of machines to run it on, maybe you can post the VI on the forums and see if other people will run it for you. You might also be interested in pulling out data like how much RAM is available, how much processor was available, the CPU usage, different things like that you can pull out of the OS. So here's kind of the overall setup that we recommend using. Drop down a for loop, put your sub-VI in it, and that sub-VI then is going to contain the code you want to benchmark. And that sub-VI then is our flat sequence structure with our high resolution relative time, and then the code in the center. So everything is fed with controls rather than constants as you feed them in through the for loop. Set up the for loop for the number of iterations you want to run. Run your code. You're going to get the results out. Coming out of there is our time difference, and that's what's building the array on the edge of the for loop. We're using the delete array element function to get rid of that first run, and then we're calculating the average, taking the min and the max, displaying those on the front panel. So again, following those basic rules, you're going to get pretty good results most of the time. Benchmarking is a little iffy. Nothing's going to be absolute with this. So and don't do your survey yet because we have Christian coming up. That's all I had. Like I say, my part was pretty quick. The presentation is available online. So I'll give Christian a quick introduction here as we switch things over. Go ahead.
You don't have to worry about that counter rolling over like the other millisecond counter. You have to worry about it rolling over.
No, absolutely.
It's a double precision number, so we shouldn't get any rollover. The biggest thing is the clock drift on that one, but again, if you're, it's pretty far out there. So
you only have to worry about the rollover if the time is longer than what is intended to the power of.
What does it start at 0?
It doesn't matter if it starts at 0 if it rolls over. The way integer math works, the difference is still correct.
Oh.
Yeah.
Yeah.
No, it's based hardware. On most systems, it's hardware based on a 64-bit counter under the hood, and that 64-bit counter is not going to roll over for like a few hundred years, basically. So, like cruising. So hopefully you're not.
There's the only problem if you try to measure something that's longer than how many days it has.
That's hundreds of
Yeah.
years.
For that, it's hundreds of years.
Yeah, so it shouldn't really be a problem.
Yeah, I would really good for that.
Yeah.
Go ahead.
Yeah, are there cases when you would not want to do the inline option for the sub-VIs?
Doing the inlining is just kind of a development or an architectural choice, really. It's not it's not a function that I use a lot personally.
There's some functions you don't want inline.
Yeah.
You've got an uninitialized shift register that's not supposed to be the that'll have different.
Yeah, sometimes you can't just based on what it's doing.
It's more an edit helper. It cleans up your diagram, but the code is actually part of your main diagram.
And
it's just isolated to edit it separately.
And there may be instances where that dead code elimination function would get rid of code even if it's not in line. This was just an example we had that we knew worked. So, regardless of how you have it set up, you may need to watch for that.
And every year it gets harder because the compiler gets better.
The compiler gets either smarter or trickier, yeah. They change it all the time on us. Anything else before Christian comes up? One more?
Yeah, so you've shown it with the high resolution there a reason it was inside the sub-VI and not just inside the for loop, but outside the sub-VI?
Do it either way.
Yeah, either way should work. If you do it outside, then you're also including the overhead call of the sub-VI itself. So if you want to know what that is, then yeah, you can put it outside. No. No, yeah, that was one thing that we didn't cover in this at all, is like the desktop execution trace toolkit, or just the profile VI tools that are in LabVIEW.
Would you recommend a default precision for the high resolution relative seconds? I mean, is there like a start here, or do we care about nanoseconds in that?
Don't believe the 14. I will tell you
Yeah.
unequivocally, don't apply the 14 digits of resolution. I don't know why somebody would write that in the help and think that you have like anything doing with like tens of femtoseconds.
Yeah, I wouldn't believe the accuracy of it. The 14 digits are there, but how far out you can actually usefully use is probably a question for him.
Usually, yeah, if it's more than tens of nanoseconds on like the absolute fastest, but usually the things you're benchmarking, you're going to see, you know, hundreds of nanoseconds, microseconds.
Yeah.
An SI display on the results is double. Like,
Yeah. All right, so here's probably the reason most of you are here. Christian Altenbach is going to talk about optimization, and regardless of what you might think of him and his 10,000 plus posts on the forums, he did 30,000 now. Yeah, he does actually have a job. He works at the UCLA Stein Eye Institute as a researcher, doing probably some very interesting work there. So with that, I'll hand it over to Christian.